I'll be talking about emulating Space Invaders in React, because everybody thought about doing this, right? Okay, who am I? I work at PayPal. I'm a front-end engineer. I work with Kent C. Dodds. Woo! Is he here? No? Okay. All right. This is my Twitter handle. I know you're tired, but let's try and stay awake. This will be exciting. These are my two twins. I have 5 kids. These are the last 2. Hopefully the last 2. This is my daughter. This is my son. I tend to just grab whatever PJs I can find. Drives my wife crazy because he's wearing her clothes. All right, so why would you build an emulator like this in React? Or why would you build an emulator, period? So about a year or 2 ago, I was interviewing at one of the big Silicon Valley companies. One of them wrote a fancy framework that was talked about today. And I was in the final stage of the interview, and I got farther than I expected, actually, but I was doing pretty good. And then it came down to whiteboarding and sorting algorithms and big O and efficiency. And I'm not a CS major. I studied IS in school, so every step of the interview, big O came up, and I was just like, okay, I need to learn this big O thing. So I failed the interview, and it caused me to kind of widen my gaze a little bit and think, okay, are these principles actually valuable? Are algorithms, CS principles applicable for front-end people, and is there any value in learning them? Because front-end folks, we tend to like things in a nice, neat package API, and if it's not that way, we're like, nope, too complicated. I'm not gonna deal with this, right? So it forced me. So then over Christmas break, I was playing this old DOS game called Colonization. Has anybody played this? 1 hand, 2 hands, okay. And in order to play this on your Mac, it's basically like Civilization, but in the colonial time, you can settle the Americas, choose whether you're nice or not, things like that. It's a fun game. But in order to run this on your Mac, you have to run this on an emulator. The one I use is called Boxer, which runs DOS games. So I started thinking about this and started thinking, okay, how does this work? This seems magic. And so I started Googling and found a bunch of blog posts that talk about Chip 8. That said, if you want to build an emulator, this is the simplest one you could start with because there's a small instruction set. So I started looking around. In 1978, this is what a Chip 8 game looked like. So this is a game called UFO, and we'll be looking at that today. This thing has 4K of memory, so that's very tiny. Our modern computers have 16 gigs of RAM, so 4,000 versus 16, what is that, million? Billion? I don't know, somebody do the math. Oh, I forgot to say, I never get pictures of me speaking. If somebody can snap some pictures during and send it to my Twitter, that'd be great, but if you want to listen instead, that's fine. Okay, so let's start talking about what is an emulator. So an emulator, essentially, you're building a program that can run the original compiled code for a different system. So usually when you have compiled code, it's specific to an architecture. So if you have a 1978 system, it's going to run on that system. It's not going to run on my modern system. So our job is to take a Chip 8 game like this and be able to run it, any game, in a modern browser. That's our task here. So building a Chip 8 emulator in 7 steps. Step 1, get the game source. So if you ever want to emulate or play an old game like a DS game or a Game Boy game or a NES game, you usually have what's called a ROM burner, which you can feed your cartridge into, and it will read the binary off of that, and then you can save it to your computer. Thankfully, I didn't have to do that because there's Google, and lots of other people have done this sort of thing. So you just Google for Chip 8 ROMs, and there's a bunch of options here. So we'll start with the simplest one. We'll start with Pong. Has anybody played this? Yeah? Okay, wow. Lots of hands, okay. I didn't realize, okay. Okay, so Pong, super simple. Let's download that instruction set and try and open it up in our text editor. All right, Has anybody tried to open up a file like this and this is what they saw? Basically, any non-text file, it's going to show this, which is basically gibberish. And so I started thinking about, I said, okay, what if I open this up using Node? Oh, sorry. The next step is that we need to transform the source. So if we do an fs.read file sync of Pong and then console log it, it gives us this buffer, which is a little bit more human readable. It's hexadecimals. Okay, but what exactly are we looking at here? See, these are machine code instructions for a computer. But the important thing to note here is that the first instruction here is 6A. So 6A and 106 and 1101010 are all the same number. Okay? This is the hexadecimal version, which is base 16. This is the base 10 version, which is what we use. This is the base 2 version because it's binary. But these are all the same number. And this is a machine code instruction for the CPU. So how do we get from this game logic to a running game? I made this half an hour ago in like 5 minutes. So we have these machine code instructions, which we feed into a CPU, and there's a CPU loop that runs, which then instructs the video or the sound. Oh, that's my wife saying good luck. That is perfect. So the CPU sends a signal to other parts of the hardware, usually. It says, okay, I want you to draw 10 pixels on the screen at this location. So it sends signals for video to the video card, for sound to the sound card, and it listens to input. So we're going to do all this part in React, but you could replace this with a terminal, native app, an Android, an iOS app, anything you wanted to. And we're going to write this part in JavaScript, and we already have this. So how can we learn about what the chip 8 system, how the internals work, and things like that? So we can go, we can go to Wikipedia. So it talks about the memory setup. The most important part here is that the program usually starts, the first 12 bytes of memory are saved for the interpreter. So that means we need to load our program after address, after memory sub 512, which is this is the hex address for that. A CPU has something called registers usually, which is basically a fancy way of saying variables. It has set variables that you can store things in. The most important part down here, though, is what are called opcodes. Zoom in a little more. So we saw 6A was the first one, and it's 2 instruction sets, so 2 of those digits are 1 instruction. So 6A02. It's going to be this one right here. That just means set the variable Vx to whatever NN is here. Okay, so a little bit magic, but there's some C pseudocode here, and it's the type of assembly call that's made. Most of it's math, some of it's flow. This one, yeah. Okay, let's go back to our presentation. Okay, so the next step is to load the game. So here we have Pong. This is the entire logic for Pong. Okay, 486 bytes, or 4 something. Math is not my strong suit, obviously. So we have Pong here. And then we have a simple React app, a React component. So here's the Pong. So the first thing we're going to do is initialize memory, which is 4K, but we're not going to fill up the entire thing. But it can be up to 4K. Actually, that should be this memory. And then we load the game. So we start at memory address So this is how you write hexadecimals in JavaScript. If you type this into a REPL, it'll give you the 412 number, the 512 number. So if you ever see 0x, that means you're dealing with hex. So we're starting at 512. So take the Pong up there, load it into memory at 512, and then we load it all in. Okay, next we need to talk about the emulator state. It talked about registers, things like that. I'm going to glance over this quickly-ish so we can move on to the more exciting stuff. So V is basically 16 variables. You have this array called V. You have 16 variables you can store stuff in. The thing is, you can't name these variables because space is very constricted because you only have 496 bytes and it's a 4K system. And so you might store the score in sub 5. And you might score the position of the flying thing in sub 10 or something like that. So things are swapped out. This is, where should I draw the sprite from? This is the program counter. What operation am I reading? So it starts at 512. So this will start at 512, and then it reads the next instruction, etc. We have a screen array for each pixel on the screen. So this is going to be 64 by 32. Somebody do the math. Then we have a keys array, which is all, so this one's going to be all 0. If it's a 0, there's nothing on the screen. If it's a 1, we'll have a colored dot there. Here we have 16 zeros, which means these keys haven't been pressed. If one of them has been pressed, we change that to 1. Then we have some timers for timing. So if the game wants something to happen in 60 seconds, or it won't be 60 seconds, in 1 second, it'll set this to 60 because it decrements at 60 hertz, meaning 60 cycles per second. And then we have a sound timer. So whenever that goes to 0, there's going to be a beep. Okay, so step 4, emulating the CPU. A bunch of code here. So if you've ever written a game, who's written a game before? Okay, there's usually a game loop, right? So similarly here, we have a CPU loop where it's running, and each cycle, you're processing another instruction. So the most important part is this. We're basically doing some bit shifting. So one of the blog posts that was talking about this, it was a CS major or a CS student. And he's like, this is a simple one to write. Should only take you a few days, but you'll have to learn bitwise operations. And I was like, okay, how hard could this be? It was much harder than I thought it was going to be. But we can learn hard things. So this grabs the current operation that you want to run from memory, which we just loaded with the game logic. And then it executes it, which I'll show in a minute. Then it runs the timers down to 0. So remember, 60 hertz, which means it's going to run down 1 cycle per second. Sorry, 160 cycles per second. If the game's paused, just stop, and then kind of keep looping. Okay, let's look at one of these instructions. So we talk about 6A02. This is what it actually looks like. So basically, if an instruction starts with 6, we're going to extract these and assign the x to the x variable. Assign this. So if it's 6A02, like this, we're going to turn this into x and this into nn. So x equals a, nn equals 02. And a here is going to be the hexadecimal, which is the number 10. Thank you. And then we store that. And we have to do parse int 16 because this is a base 16. And so we then pass it here. And every cycle, we're going to increment the counter by 2. So we go on to the next instruction. Clear as mud? Yeah, exactly. Okay, now we'll look at some code. Okay, so I built this emulator. It works. So let's pause this because it's running too fast for us to know what's happening. I just wanted to show you what it looked like running. Okay, I can actually zoom in a little bit. Okay, so we have this is our game right here. And I'm switching from Pong to something else because Pong's kind of boring. So this is a game called UFO. And here's the whole game. It's pretty short again. Here's our state we talked about. And then we're going to play one frame at a time. So the first instruction here is A2 CD. And we're at spot. The PC counter was at 512. And it's going to run this, which means load I with A and NN. The value of register I is set to 2 CD, which is hex, and in base 10, it's 717. So we increment one cycle. It's populating these variables over here. Next one, right there. Okay, so now we have a draw instruction. Okay, so this instruction here, D9A3, means draw, and the 9 is going to be X, the A is going to be Y, the Y is going to be A. You know what I mean? Okay, so this instruction drew this to the screen. So we run the next one. We're updating the state again, updating the state again. You can see these values updating here. And now we draw scroll up, we draw the second UFO here. We keep updating the state. We're drawing this. So this is an interesting one. This 2NNN, call address, call at subroutine. So this is how you do branching logic on a very limited system. You essentially say up here, okay, now go call this area down here and loop a few times until I'm ready to return, and then we're going to go back up here. And the return point is stored in the stack here. Okay, so now we're drawing the score. Okay. Now we return from the subroutine because it looped 3 times to draw the score. Now it's going to the other subroutine and it's going to loop over here. And now it's drawing that, so that's the score, 0. Actually, that's the score, and that's how many rockets you have left. Okay. Should we play this at full speed now? Yeah? Okay. All right. Okay, so this game is called UFO. You have 3 keys. You have the 5 key, which shoots the rocket straight up. You have the 4 key, which shoots it this way, and you have the 6 key, which shoots it that way. So we're going to try and hit one of these guys. I'm going to hold down 5, which changed the value here on keys. And if I hit this guy, oh, so close. Oh, maybe that guy. Yes. Okay, so now the score updated to 15. I have 14 rockets left. And you can see over here, we have a 15 and a 14. So that's where those variables are being stored. And you can see here, it's just going crazy. Let's try to hit another one. Right there. Go, 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 go. I think I'm going to miss it. Oh! The frame rate's pretty slow because I'm reading so many things in my debugger here, but you can speed it up. Maybe we'll try a diagonal attack. Go, go, go. It's so slow. Nope. So our score is 15. We have 13 rockets left. Let's shoot a few more because I'm not bored of this yet. And I have a captive audience. Oh, missing again. No. Okay. So to sum up, we've got the instructions being read here. And each time one of these is read, we update our state. When there's a draw instruction, like these, it's moving so fast you can only see the draw instructions. It'll spit out what's in screen here to the screen here using React render. And every time it executes, it jumps ahead one, and looks like right now it's operating a subroutine or something because it's just going crazy. I'm not doing QA, but any questions here? Anything you want me to explain briefly before we move on? No? Okay. Yes. That's a great question. So I don't know which one it is, but let's try and find out. So, looks like this one here is probably this or this. So it should be X and Y. I think Y is from the top. X is from the left. So I'm going to push the rocket, and you watch and try and tell me which one it is. These two, right? Yep. Because both of these, X and Y, are decrementing. Good question. Anybody else? Let's do that right now. Thank you. Great question. Okay, so let's do Pong. So I'm going to go right here and full screen this. Okay, so I have UFO right now. So let's just replace this with Pong. And we got Pong. So again, you have the same instruction set, different order, but essentially the same things. The variables here mean different things, but you have Pong running. Again, it's slow because of everything I'm doing, and now it's 1-0, and it's going to keep running. A more complicated game, which has a much bigger instruction set, would be Space Invaders, which is what this talk is actually named on, but so you can see here, there's Blinky, which is a Pac-Man, early version of Pac-Man. Then you got Invaders, which is also pretty big. Okay, so here's Space Invaders. Oh, it's going to be so slow. But look, they're drawing text on the screen. They have sprites for words, and then it scrolls over. Normally it's not this slow, but. So this is pretty fancy for 1978, right? You have single pixels. You have a 4K of memory. It's pretty impressive, you know? But in order to code this, you have to write all these instructions, which I wouldn't want to do. Okay, any other questions? Great questions. Okay, let's move on. All right. So, step 5, emulate video output. We'll start with this note. So, I hit a bunch of the code here, but basically we have the screen, which is an array. If it's 0, it doesn't draw anything. If it's 1, it fills it in with the red. Then we have this game canvas down here, which takes the props, which looks something like this. If it's 0, I add a class name of pixel. If it's 1, I add a class name of pixel active. And then we just render that to the screen. And I used CSS Grid, which is amazing. Who here has used CSS Grid before? Wow. I hadn't used it until a few days ago. And now, this is CSS Grid, this is CSS Grid, and this is CSS Grid. So CSS Grid, all the things. Okay. So the really nice thing here is I was able to so easily say, make each row 64 pixels wide, 64 items wide. That's so hard to do if you don't have CSS Grid. Okay, let's talk about rendering per for a second. I'm going to actually open up the code for this, because that's easier. Okay, is that big enough? Let's go a little bigger. How's that? Is that big enough? Looks a little blurry, but. Okay, so you might have noticed that I'm not using this .state. That's because if I used setState in React, it would cause a re-render every time I update state, right? Which at 60 updates or cycles per second, I don't want to render that often. That would bring my game to a crawl. So I just named this mState and said, don't re-render when I update my state. It's not fancy, it's just an object. So then, we have our game loop. And here I've done several things. So there's an opcode. As part of the draw opcode, we set a draw flag where it says, right now, I updated my screen, I want you to draw now. And so when we do this, at that point, I update set state, and the value of this really doesn't matter. It's just, hey, React, please render because I did something. And so then we're making an update to React, which forces a re-render, and then I run the CPU loop again. So when the draw flag is set, run again. If I want to speed this up, I could consider only updating on every other draw flag. You might miss a few things here, but it really speeds things up. Okay, let's go back. Okay, let's look at the opcode real quick, because I know you want to be overwhelmed. Okay, there we go. Okay, so here's the opcode for drawing to the screen, which really all this is doing is it's taking the state and it's saying something's changed, now change what's in my screen array. So bitwise operations, fanciness, it updates it. It sets the draw flag to true, and it increments the PC counter. Any questions here? I probably won't be able to explain it, but any questions here? All right. This part I had to steal because I wrote it myself, and there were all these weird bugs of like the screen wouldn't line up, and at one point it was rotated the wrong way. I was like, ah! So you messed this up and nothing's working basically. All right, but to me it's really cool that they're using this both as collision detection and for drawing pixels on the screen. So it's actually using this as state to know, okay, has something happened? Should we increase the score or end the game? Okay, so step 6, when we're almost in here. Emulate sound output. So this is the opcode for sound, which basically we parse out this. So this gets assigned to x, and then we set whatever is stored in the v sub x variable. So if it's f2, it'll be v sub 2, and that gets assigned to the sound timer, which means make a beep in 2 cycles. And this is how you make a beep using web technology. Nothing too fancy, it just makes a beep. Okay, emulate input. Okay, so we can use React here, but really you could use anything. We have a key map. I'm using keys 0 through 9, and these, not QWERTY, but QWERTZ. And for a chip 8 system, the keyboard, it was 0 through 9, and then A through F, I think, so hex essentially. So if this key is pressed, update that position in the keys array. And then there's an opcode that checks, has this key been pressed? If it has, skip an instruction, or skip 2 instructions. Then we reset it just by filling them all back in. We have 2 global listeners. Okay, so let's look at it again real quick. Pretty cool, right? I mean, you have Space Invaders running. We have an emulator now that we can feed any game into. And if we remove all this stuff, then it actually runs fast enough. So where to from here? For a hackathon, some folks at Netflix decided to run House of Cards on an NES. It's pretty cool. So you could use these principles basically and just downsample. So you have your video bits, which would just be an array of streaming data, or lots of streaming data. And I think what they did is they took an NES cartridge and programmed it and loaded the data on the cartridge. So they actually put it into the NES system, and it then played House of Cards with 8-bit sound. So pretty cool. There's this guy who wrote, there's jsnes.org. I should include a link, but basically you can run, let's just go there. You can run several NES games in your browser. And if you look at the code, I was able to type that blind. Nope. So you can come here and you can play, these old NES games. And if you look at the source, it's based on the same principles. You can go in, there's opcodes. There's the rendering logic is way more complicated because this isn't just big blocky pixels, but it's based on the same principles, which is pretty cool. That's it. Thank you.